Okay. Oh, and if you drop an object near the Earth, and I'm being fussy because as you move further from Earth, gravity changes, but near the Earth, objects in a vacuum, if we ignore air resistance, they'll all fall to the Earth with the same acceleration. In a vacuum, if you take a feather and a hammer, they will fall at exactly the same rate, regardless of their mass. So I wrote here, yes, a feather will accelerate at exactly the same rate as a bowling ball. Put your pencils down. We use a lowercase g for gravity. Andrew's going to put her phone away because she's just not that important. We use a lowercase g for gravity to represent the strength of the Earth's gravitational field. G for gravity. And g is, as a magnitude, 9.8 meters per second squared. It varies a tiny bit because the Earth is not perfectly uniform inside. So I've seen as 9.79 up to 9.801. There's some variation, but 9.8. If you want to add a direction, you can, Ethan, put a negative there and make it down as negative, but as a magnitude, it's that. By the way, what's a nice round number that's really close to? 10. So if I'm ever standing in line, say at a ride, and I'm trying to calculate how many G's that I'm going to experience at Playland, and why wouldn't you calculate that while you're standing in line? Because it adds to the ride. I use 10 as my rough number. In fact, people talk about G forces, which is a pet peeve of mine. It's not a force. G's are a measure of acceleration. They should be talking about G acceleration. So you'll just hear me talk about G's. I'll almost never say G force. Not a force, it's acceleration. So 1 G is exactly 9.8 or approximately 10. 2 G's is exactly, I think it's 19.6, double check me, approximately 20. 6 G's is 9.8 times 6. Well, it's going to be 60 minus, sorry? I was going to do it in my head, but okay. It's right around 60. Outside of a vacuum, air resistance can cause an object to accelerate slower. So if you drop a piece of paper, it is going to flutter down to the ground. But in a vacuum, it'll just drop like a rock, like everything does. But we're going to ignore air resistance most of the time. So almost always, because air resistance is a very difficult thing to calculate, you'll hear me say, just imagine it's a very aerodynamic bowling ball made out of lead, or a cannonball is a good example. Human beings can survive up to 25 Gs in most situations without dying, although anything over 10 tends to break ribs and bones, and those are kind of the shock absorbers of our system so that more damage doesn't occur. Playland, the highest ride, is approximately... Which ride? Assuming that we're back to normal next year, if you take Physics 12, in May we go on a field trip to Playland with accelerometers and other instruments, and we find out. How do we know that human beings can survive 25? And how do we know that 10 breaks bones? A lot of our data comes from a series of experiments that the U.S. Air Force ran back in the 1950s and 60s, and it was headed by Air Force Dr. Colonel John Stapp. He was in charge. He could have ordered the people beneath him to, quote, volunteer for the experiments. He didn't feel comfortable doing that, and so he volunteered for a lot of the experiments himself. I'll be showing you some live video in a few minutes, but he was involved in designing and testing ejection seats for jet fighter pilots. A lot of our crash test dummy data also comes from these experiments. He rode a rocket sled that ran on a special track. He was subjected to 15 Gs for 0.6 seconds and a peak of 22 Gs during this photo. He's pulling about 22 Gs. However, his all-time record, he was traveling at 0.9 times the speed of sound, which is Mach 0.9. It was around 300 meters per second. He came to a stop in 0.68 seconds. How many Gs did he experience? If I ever ask you to find how many Gs, and I will, first you're going to find the acceleration. So A equals question mark? What's that 300? What's that 300? Which one? Someone said VI, someone said VF. The good news is one of them's right. What's VF? Okay, so VI is 300. VF is 0. What's that 0.68? I'm looking for an equation that has an A, a VI, a VF, and a T in it. There is one. Get the A by itself, please. I'll give you a hint. A equals. So it's going to be 0 minus 300 all over 0.68. Which is what? You're going to get a negative answer because he's slowing down. Negative 441 point blah, blah, blah. I'm going to write negative 441. Now that's an acceleration. That's meters per second squared. This asked how many G's. To figure out how many G's, you divide by 9.8. Because it's asking how many 9.8s would fit into there. So G's equals, I'm going to write negative 441, but Aiden, I'm going to use my answer button on my calculator. Divided by 9.8. $45 G's. And the units for G's are G's because it's actually meters per second squared divided by meters per second squared, and so it's no units. To put things in perspective right now, can all of you sitting in your chair lift your feet off the ground? Right now, you're all feeling 1 G against your chair because all of you are feeling your own body weight. So 45 G's would be 44 of you dogpiling on top of yourself. That's 45 G's. All of you deal with 1 G all the time. Add 44 more, that's 45 G's. Okay. In another experiment, so the problem was when we first built jet airplanes, the question was it even worth putting ejection seats in them? Because if the pilots would die ejecting at those speeds, then your best bet was to force them to maybe try to land the plane, because at least then they might survive. So this was how they ran the experiments. And then the other question was, okay, even if they survive, if they eject at that speed, will all the skin off of their body get ripped off? So he also exposed his face to 940 kilometer per hour winds in another test. Okay? Put your pencils down, look up.